We advanced talking about length, areas, and volumes by considering circle theorems. I deem it fit to consider this, having talked about circles previously, and of course, even solid shapes built on circles like cylinders, spheres, cones, and all of that. So let's see what circle theorem is about. Circle theorems are about the goal is to learn the standard circle theorems and apply them in angle chasing problems. Okay, so the key terms here will be things like circle with a center O, having a radius and a diameter. Then we talk about the chord of a circle, like and which is the line segment joining 2 points on the circle. Then we have the arc, which is part of the circumference. We have tangent, which touches circle at exactly 1 point. We also have secant, which cuts the circle at 2 points. Then there's also cyclic quadrilateral where whose all four vertices lie on a circle. Then we have angle fact that we always use, right? The fact that angles in a triangle add up to 180 degrees and angles on a straight line add up to 180 degrees. And of course, vertically opposite angles are equal. So let's look at some of these ideas here. So first of all, imagine you have a circle whose center is O, right? And then, of course, this circle now has what you call a radius. A radius, that's the distance from the center to any part of the circumference of the circle. Then, apart from the radius, we also have what we call the diameter, which is twice the radius. So this is the radius, and then it continues like this. So the diameter is actually 2 times of the radius. So it starts from one part of the circumference of the circle to the other end, passing through the center. So that's diameter. And then we have arc. So imagine that we emphasize this part of a circle now. Uh, is that a nice way to look at it? Let me do it another way. Um, okay. Let's go black now. So imagine if I get this portion out, this portion of the circumference of the circle. So this is an arc now. This is an arc. Interestingly, there are usually two arcs, you know. So there are usually two arcs. The arcs so the smaller one is the minor arc, while the bigger side here, this whole big thing here is the major arc. But let's focus on the minor one for now. So that is an arc. It is a portion of the circumference of the circle. Apart from that, we have what is called a tangent. A tangent touches a circle just at a single point. Imagine that this point here, we want to look at a tangent. A tangent to this point will be a line like this. Sorry, this one, a line that just touches that point like this. It doesn't cut the circle. So this is a tangent right here. And then apart from tangent, there's the idea of a secant. A secant is a line that cuts through. So a secant on its own hand will cut through the circle. So a secant cuts the circle at 2 points. So if I have a line like this, so cutting through the circle at this point and at this point. So for a tangent, it's just a single point, but a secant cuts through the circle at 2 points. So this is a secant right here. Okay, and then there's a cyclic quadrilateral. So if I draw another circle with center O now, a cyclic quadrilateral will be that four-sided polygon, any four-sided polygon whose vertices lie on the any four-sided polygon whose vertices lie on the circle like this. So ABCD now, this thing now, you can call it a quadrilateral, cyclic quadrilateral. And having talked about that, we would also want to talk about some angle facts, angle facts. Now we've used this a lot previously. So the first fact is that angles in a triangle add up to 180 degrees. So if you have any triangle at all, say this one with angle A, B, C. Let's say this is A, B, C. So we say that angle A plus angle B plus angle C is equal to 180 degrees. So we have that. So another fact about angles is that angles on a straight line add up to 180 degrees. Imagine this straight line now, and you have this, this, and this. So, as many as possible, as far as they all lie on the straight line. Okay, as far as they all lie on the straight line. So you can say that this may not look straight, but I mean, assume it is straight. So this is alpha, beta, gamma, delta, and epsilon. So because they're all on a straight line, let me draw the straight line properly so that it will be to make a bit of sense. Yeah, something like this. So we can say that alpha plus beta plus gamma plus delta plus epsilon is equal to 180 degrees. So those are some preliminary things we need to know. Now, having said that, let's go back and start looking at the theorems one after the other. So look at the first theorem. It says that, okay, the first theorem is about, theorem one is about angle at the center is twice the angle at the circumference. So the statement is that for the same arc or chord AB, if AOB is the angle at the center and ACB is an angle at the circumference, standing on the same arc AB, then angle AOB is equal to twice angle ACB. And the typical use is you are given one of these angles and asked for the other. Now imagine when we talked about an arc the other time. So anytime you draw an arc, anytime you have a circle, right? Anytime you draw a chord like this and you name that chord AB, so it automatically cuts out an arc like this. So that's why we can refer to the arc AB or chord AB, anyhow you want to refer to it. So you can say chord or arc anytime, but usually we talk about arc for the most part, right? So now that's what the statement. So the statement now is saying that if you have this arc AB, of course, the circle has center O. So if this arc or this chord AB makes an angle at the center here, which is this is angle AOB now, and then the same arc or chord now goes to some part of the circumference and makes an angle ACB. So what the theorem is saying is that angle A angle AOB is equal to twice angle ACB. So that's what the theorem is saying. Now, and we have the proof here, but I'll just read through this and come back to that page. So imagine if chord AB subtends angle AOB at the center and angle ACB at the circumference on the same arc AB, then angle AOB is equal to 2 angle ACB. So the proof, so we can have a standard proof using isosceles triangles. So we can join OA, OB, and OC. And since OA is equal to OC, triangle AOC is isosceles. So okay, well, I mean, instead of doing this, so I'm going to go through this idea while I demonstrate it practically on the worksheet. So let's go. So imagine now that we have this setup and we just want to prove that. So the first thing is this. We want to show that angle AOB, this angle AOB made in the center is twice angle ACB made at the circumference, at another part of the circumference on the circle by the same arc AB, or if you like, chord AB, like this. So what do we do first of all? So we say that we join OA, OB, and OC. Join OA, OB, and OC. So of course, I think I've done that already. Join OA. This is OA. This is OB. So I didn't join OC. So this is OC now. So that's that. So you can see that this is radius, and this is radius. So as a result of that, we have three isosceles triangles right there. So we see that since OA is equal to OC. So you can see that this OA now is equal to this OC. And it's also even equal to OB. So since OA is equal to OC, then we can say that triangle AOC, this triangle AOC right here, is isosceles. Of course, it's isosceles because this side is equal to this side because they are both radii, right? So triangle AOC is isosceles. Okay, so and if that is the case, if you then say let OAC, this is OAC. So if you let this OAC, angle OAC will have to be equal to angle OCA because Now, this side and this side are the same. And we know that base angles of isosceles triangles are equal. So if you say this is equal to x now, they are equal and they are equal to x. In the same way, since OB, this OB is also equal to this OC. So we can have the same idea, right? So also OB is equal to OC. And then that means that triangle BOC is isosceles to, okay? Triangle BOC is isosceles. And then we say angle OBC is equal to angle OCB, and that is equal to y. So we're saying that angle OBC, this angle OBC is equal to angle OCB, same here, all right? And we say that is equal to y. So in that case now, then the angle at the circumference ACB, so this angle at the circumference, which is ACB, this angle ACB right here, can then be said to be, so we can say that angle ACB now is equal to the addition of these two angles. So this angle ACB will be equal to this angle right here, ACB, these two of them. So you can see it is the addition of this angle plus this angle. And then we already know this angle is one of these two. So uh so ACB now can be angle OCA plus angle OCB. That's like X plus Y. You see? So this is, so like we said, this is X, and this is Y, this is Y. So this angle ACB is X plus Y, as you see that there. So then we can now consider the central angle. So for the central angle in triangle AOC, so in this triangle AOC now, this angle right here, AOC, we can say that is equal to, so because X plus AOC is 180 degrees, so we can say that angle AOC is equal to 180 degrees minus X plus minus X, that's 2X. So and again in triangle, so we also see that angle BOC, same thing. Look at BOC now. Angle BOC, this angle right here, will be 180 minus 2y. That because this angle plus y will be 180. So that angle will be 180 minus 2y. So BOC is 180 degrees minus 2y, like that. So you can see that angles around point C. So angles around point O here, around the center, will add up to 180 degrees, as you already know. So this angle now plus this angle plus this angle will add up to 100 and will add up to 360 degrees. That's angles at a point. So in that case now, we see that angle AOB, okay, so now angle AOB is equal to 360 degrees minus angle AOC, this angle AOC here, minus angle BOC also. So angle BOC, like that. So that means we simply have 360 degrees minus 180 minus 2x. This is 180 minus 2x, then minus 180 minus 2y. So in that case, we have 360 degrees minus 180 plus 2x minus 180 plus 2y. So we see that 360 will cancel out all of this. So we have 2x plus 2y. So here we see angle AOB is 2x plus 2y. That means angle AOB is 2 into x plus y. If you remember what we did the other time, we discovered that you see this angle ACB now is actually x plus y. Okay, we saw that here. So angle ACB is x plus y. Okay, so we can recall that. So we see this is 2 x plus y now is angle ACB. Uh so angle AOB now is simply 2 times angle ACB based on what the theorem says. So that's just what the proof looks like for that first theorem. Okay, so we come back here now. So, I mean, this is what I went through, and thankfully, I've demonstrated it practically. So, you may want to relax and look at it again to see how we came about the proof. So, if you want to take worked examples, it's pretty easy. Since the proof has been established, it's just easy to know that, oh, so a chord subtends angle ACB, which is 38 degrees at the circumference. Find AOB. That's the angle at the center. That'll be 2 times 38, and you have 76, even without drawing the circle itself. Then if angle AOB, that's the angle at the center, is 124 degrees. Find angle ACB. Just divide this angle at the center by 2. You get the angle at the circumference. Multiply the angle at the circumference by 2, and you get the angle at the center. And that's how that goes. So we move on to the second theorem. So for the second theorem, angles in the same segment is what we are talking about for the second theorem now. Angles in the same segment are equal, okay? So if points C and D lie on the same segment of the circle subtended by chord AB, right? Then angle ACB is equal to angle ADB. So quick recognition, two angles standing on the same chord AB and on the same side of the chord are equal, right? So let's try to visualize what we're talking about there. I think I need a brighter color apart from this one. So let me go change. Can we rest black for some time? Let's change that to say, which one now? Which one? Okay, let me go for this. Okay. So now we're saying that angles in the same segment are equal. So we have a circle like this, right? So with that circle in place, if point C and D lie on the same segment of the circle subtended by a chord AB. So let's say we have a chord AB, if you like, call it, okay, I mean, it's chord this time around. So we have chord AB and C, you have C here. This is C and this is D. And you have this line, you have this line. So the chord makes this angle here, and the same chord makes this angle here. So that angle, we're saying that angle ACB is simply equal to angle ADB, or if you like, angle ABD. Angle A, no, angle ADB. Yeah, angle ADB. So that's what we're simply saying there. So because both of them are sitting on the same chord AB, like that. So if you have more angles, in fact, if you have if you have an E, you have an E like this, that's still, as far as it is subtended by the same chord. So even this now is still equal to angle AEB, anyhow you look at it. So that's what this is talking about. So how do we prove that? So if we want to go for the proof, we see here that we see that if C and D are on the same segment, okay, I mean, that's the statement of the proof. So chord AB, so you can see this chord AB now. Chord AB subtends the same central angle AOB. So if you have an angle if you have a central something here, this AOB right here, okay, like what we learned not quite long. So okay, or better still, we say this is center O. So you see this angle will come like this. So this is our angle AOB now. So this chord makes this angle at the center. So if we go by the proof, by the first theorem, then we can simply say that since this same arc subtends this angle AOB at the center, and then it now subtends all these other ones at the circumference, automatically those other ones will be half of what you have at the center, right? So let's see how we can systematize that a little bit. So it is established, right, that angle AOB from the previous theorem is 2 times angle ACB, and it will also be 2 times the other ones. So it will be 2 times angle, it will also be 2 times angle ADB, and of course 2 times angle AEB. Anyhow you look at it, that's what it should be. So also for point D on the same circle, okay, I mean that's the idea now. So in this case now we just simply see that AOB is equal to all of this. So it means that all this are simply the same. ACB is equal to ADB, is equal to AEB. So if you, as far as the chord is making the angle at that side, then that is always true. Okay. So with that in place now, we can then say, we can go for the worked examples. So if ACB is 57 degrees, find ADB, right? So it's the same thing we have up here now. So ACB, we are now saying that this ACB is 57 degrees, and we're looking for this, I mean, we don't have to look too far. X is equal to 57 degrees easily, and that is A angle ADB easily. So based on what we have established from the statement of the theorem and its proof. So that's just that. Then another thing is, I mean, following the same triangle, right? We now have that angle ACB is 3x plus 10. And angle ADB is 5x minus 30. Find x. Of course, we already know ACB is equal to ADB from the theorem. So that means 3x plus 10 is equal to 5x minus 30. So if it tidy things up, so we have 5x minus 3x, then 10 plus 30, that's 40 equals to x. So x is equal to 20. So that's 20 for x now. So it means ACB will be 3 times 20, 60 plus 10. So ACB is 70 degrees. ADB will be 5 times 20, 100 minus 30. That's also 70 degrees like that. And that takes us to theorem 3. So for theorem 3 now, we have that an angle in a semicircle is a right angle. Okay? An angle in a semicircle is a right angle. So now, I think you see that theorem 1 tells us that a chord or an arc, the angle a chord or an arc makes at the center of a circle is double the angle it makes at any part of the circumference. So the idea of a semicircle is simple. It's for a semicircle, the whatever you have two half chords. I mean half uh I mean that's the diameter now. The chord now is the diameter and the arcs are the semicircles. So and at the center like that, the angle is simply 180 degrees. So any other angle in any of the segments will simply be 90 degrees. So that's a very simplest, is a direct way to look at the proof of this particular theorem 3. So let's see if AB is the diameter and C is any point on the circle, then angle ACB is 90 degrees. So quick recognition, if you see a diameter, look for a right angle at the opposite point on the circle easily, right? So the proof is such that if AB is the diameter, then for any point C on the circle, ACB is 90. So since AB is the diameter, AOB are collinear, right? So angle AOB will be 180 degrees. So by theorem 1, angle AOB is 2 times angle ACB. And so 180 degrees is 2 ACB, and therefore angle ACB is 90 degrees. Okay, let's demonstrate that briefly because this is very straightforward. Imagine that you have this circle and the center is O, and then you now have a diameter like this. So this is a semicircle. Of course, this is another semicircle. And in this case, now, if you say this is AB, so clearly we know that angle AOB here is 180 degrees because that's a straight line. The diameter is a straight line like this. So now, if the same chord, this same diameter is now making this angle here. So whatever this angle is, it's 90 degrees. That's what we are saying. So if you say this is C now, for instance, so we know that angle AOB, right, is equal to 2 times angle ACB. And since we know that AOB is 180 degrees, so we have 180 degrees equals 2 times angle ACB. So that means that 180 degrees over 2 is equal to angle ACB. In all, angle ACB is equal to 90 degrees. So if you like also, whatever, if you also come here and say, maybe you have a particular, maybe call this D now, okay? And then you have, as far as the same diameter is making this is automatically right angle. So we just know that angle ADB is also 90 degrees, going by the same idea like that. So that's what, I mean, the proof is straightforward. Maybe that's about the simplest proof so far. Now, for the worked examples, example 1, AB is the diameter in triangle ABC. So angle CAB is, as far as the angle CAB is 28 degrees, find CBA. Okay, in this case now, sometimes you may not be able to do this properly if you don't really draw it. So let's draw this so we can see what we are saying. I mean, the second one is easy. If XY, as far as you don't, if you see XY at the end, you just automatically know that the Z at the center is 90 degrees. Now, the reason why we have to draw this to see what is happening is that you can see AB is not ending it. So it means that this the angle in focus is a not not as far as AB are the extremes. Like if XY is diameter now, so you know XZY. So Z is the focus, is what the focus is on. So we know that's automatically 90 degrees. But for anything that is not that where the diameter value labels are not at the first and the last, then you know you need some other kind of angle there. So let's go ahead and check that out. So the question there, that first question is saying that if AB is diameter, so we have our circle, then AB is our diameter. We already know that we have this arc now is now a semicircle. Each arc here is a semicircle. So that's what that is about. And then we have this angle CAB. So if you have so let's say this is C now. So if we bring this and bring this down, so we now need this angle now. This is the angle we need now. So already we know that angle ACB is 90 degrees. So this is 90 degrees taken. And then another thing is this. So angle CAB is 90 degrees. So we now have that angle angle ACB. We know that's okay. This is the deal. So AB is a diameter, right? In triangle ABC, angle CAB is 28 degrees. Yeah, so we have that. So now we are given that angle. So we're given that angle CAB, that's given, and it's given as 28 degrees. So we can now say that angle ACB is 90 degrees. So we say angles in angle in a semicircle. Angle angle in a semicircle. Semicircle. Okay. So with that in place now, we now need to look for angle CBA, or if you like, angle. So we're looking for angle CBA, yeah? Angle CBA is what we don't know now. So based on all we have learned so far, we know that angle, this angle here, angle CAB plus angle ACB plus angle CBA should be equal to 180 degrees. That's angles in a triangle. That's the sum of angles in a triangle. That's one of the facts we learned before we got here. So CAB is now 28 degrees. ACB is 90 degrees. So we are looking for CBA. So that should be cool to find. So we have angle CBA now. Angle CBA plus 118, I believe, is equal to 180 degrees. So that angle CBA now is equal to 180 degrees minus 118 degrees. So angle CBA is simply the same thing as 62 degrees. So this angle is 62 degrees based on what we have found now. So then we have the other question is if XY is a diameter. So imagine we have this now and XY is just a diameter like this. XY is a diameter, and we are told to find XZY. So let's say the Z is here now. So we are looking for XZY. So we know easily, I mean, without even indicating that angle XZY automatically will have to be 90 degrees. That is angle in a semicircle. Angle in a semicircle because it is subtended by this diameter. So any angle subtended by the diameter on the circumference of the circle is simply a right angle. It's 90 degrees, half of the angle at the center, which is 180 degrees. So that's theorem 3. We move on to theorem 4. So for theorem 4, opposite angles of a cyclic quadrilateral sum to 180 degrees. Okay, so if ABCD is cyclic, then angle A plus angle C is 180 and angle B plus angle D is 180. So the quick recognition, a four-sided figure with all vertices on the circle is what we call a cyclic quadrilateral, like it was shown to us before. So we have the proof right here. So angle A plus angle C is 180, angle B plus, okay. So the proof is you have same segment and straight line. So you can focus on angle A plus angle C. So angles DAB and angle DCB both stand on chord DB, but from opposite sides of the chord DB. So don't worry, I'm going to demonstrate it on the worksheet, so not a problem. So angle DAB equals the angle in the alternate segment, and that will stand on DB on the other side. More directly, in a circle, the angle standing on chord DB on opposite sides add to 180 degrees. So they intercept the full circle around that chord. Thus, angle DAB plus angle DCB is 180, such that angle A plus angle C is 180 each. So similarly, using chord AC, uh, chord AC gives angle B plus angle D is which is 180. Okay, well, that may sound somehow, but let's go ahead and demonstrate it so you can get the full gist. So we're talking about the fact that opposite angles of a cyclic quadrilateral sum up to 180 degrees. So imagine that you have that's our theorem 4 now. So you have a circle, center O, and then you now have a cyclic quadrilateral. Say this, all the vertices sitting on the circle like this. So let's say this is A, B, C, D, like that. So with that in place now, we then say, we are saying that angle A, this angle A plus angle C is 180 degrees. On the other hand, angle B plus angle D, angle B plus angle D is equal to 180 degrees, right? So the question is, how do we prove this? To prove it, we said, we say we go for this, that angle DAB, right? This DAB, angle DAB, and DCB, angle DAB, and angle DCB. They are sitting on opposite sides. So, they both stand on chord DB. So this is, imagine this is chord DB now. Um, Looking at this chord now. Okay. I don't want to make the chord a semicircle. I don't want to make it a diameter. That'll be too simple to deal with. So let's imagine the center is O here. So imagine this is chord DB. Yeah, this is, if we, I mean, if we take this now, so we know that this chord DB is going to make an angle here, okay, that is twice the angle here, okay. On the other hand, this same chord here is going to make, okay, let me follow what I have. So angle DAB, now this angle DAB, right, equals the angle in the alternate segment that will stand on DB. Okay, so this angle now will be the angle in the alternate segment that will stand on DB. Say we now have this now. Um, so angle DAB equals the angle in the alternate segment that will stand on DB. On the other side, more directly in a circle, the angle standing on chord DB on opposite sides add up to 180 degrees. They add up to 180 degrees. So this angle plus this angle will add up to 180 degrees. In fact, if this was the diameter, you can see it is easily 90, and that's 180, right? So they intercept the full circle around that chord. So we say that angle DAB, so this angle DAB plus angle DCB is equal to 180 degrees. And that's exactly, it's more or less saying angle, because A and C are in the center. So angle A plus angle C add up to 180 degrees. So that's what this is about. Okay. More rigorously, right? If we have this, if we have this now, the angle, let's say if this is alpha, of course, this will be alpha over 2. On the other hand, if we take this now and, oh, this is the center. Okay, okay, okay. We can't go that other way. We can't go that other way. So, but we know that whatever this angle is, if this angle here is beta, because that's the other one. So the angle this chord makes here, this is now going to be beta over 2, right? And we know that so normally alpha plus beta should be equal to 360 degrees at the center. But now we have, so if you have alpha plus beta divided by 2, that's 360 degrees divided by 2. So, I mean, this is my own gate crashing way of doing it. So, alpha over 2 plus beta over 2 is equal to 180 degrees, like that. So, in that case now, we see that that's basically angle A plus angle C equals 180 degrees. So, we can go the same way for angle B and D also. So, let's go ahead and so since that is established, we don't have to even worry too much. So in a cyclic quadrilateral ABCD, angle A is 103 degrees. Angle C, find angle C, of course. Angle C will just be 180 minus 103, that's 77 degrees. So because ABCD, so because we name quadrilaterals, or we name shapes, we follow a pattern. So you cannot have ABDC. So you have to go ABCD. You have to follow that thing, A, B, C, D. You can't interrupt it. And that's why A and C will always be opposite, while B and D are always opposite angles of a quadrilateral. So that is why this will always work like that. So if you label wrongly, it can cause problem. So in cyclic quadrilateral ABCD, angle B is 4x plus 15, and angle D is 7x minus D. Find x. Of course, to find x, we know angle B plus angle D will give us 180 degrees, basically. So 4x plus 15 plus 7x minus 9 is 180 degrees. So that means 11. So 4x plus 7x is 11x. 15 minus 9, that's 6. And everything is 180. So 11x is equal to 180 minus 6, that's 174. So x is 174 by 11, and that's what we have for that. So we go for theorem 5, which tells us that exterior angle of a cyclic quadrilateral says something about the exterior angle of a cyclic quadrilateral. So if a side of a cyclic quadrilateral is extended, the exterior angle equals the interior opposite angle. Okay, it's equal to the interior opposite angle. For example, if you extend AB past B, then exterior at B is equal to D. So let's quickly look at that. Can we still use the same one? Okay, I guess I need to draw another one because that's already messed up somewhat. So again, we have a circle center O, and you have an equilateral. You have a quadrilateral, cyclic quadrilateral. All the vertices touching the circle. So you can label it anyhow you like, A, B, C, D, anyhow you want. So now we are saying that imagine you extending. If you extend this AB now, okay, let me drop the B below here. So if you extend this AB like this, so you're saying whatever angle you have here is going to be equal to this one. That's what this theorem 5 is about. It says that if a side of a cyclic quadrilateral is extended, so if you extend this side now, okay, the exterior angle equals the interior opposite angle. So we are saying that if this is alpha, this will also be alpha. So yeah, like that. So let's try to prove that. The proof should be straightforward too. So quick recognition, cyclic quadrilateral plus an extended side. So this is the extended side now. Okay, so imagine if ABCD is a cyclic quadrilateral like this, and side AB is extended at B, so we extend it at B like this to form an exterior angle EBC. So let's say this is EBE now. So we now have this angle EBC. Okay. So then we see that angle EBC, angle EB. So okay, well, I mean we can even take it intuitively. So now because angle, okay, let me follow the alphabets. So first of all, you see that angle ABC, this angle ABC plus angle EBC is equal to 180 degrees, settled, right? And the reason is that they are angles on a straight line. So angles on a straight line. That's your reason. Angles on a straight line. So it simply then means that angle ABC is equal to 180 degrees minus angle EBC. So we have that. Now, because this is a cyclic quadrilateral, we also know that angle, so for being a cyclic quadrilateral, right? Being a cyclic quadrilateral, being a cyclic quadrilateral, from the previous theorem we just looked at, we know that angle ABC, I mean this angle ABC, we know that angle ABC plus angle ADC, this angle ADC now, plus angle ADC will be equal to 180 degrees. That's opposite angles opposite opposite angles of cyclic quadrilateral. That was the last theorem we saw of a cyclic quadrilateral. Okay. So now what do? We already know ABC to be this. And what we are really looking for is the fact that angle EBC is the same thing as angle ADC. So what is angle ABC now? Angle ABC is 180. So now this is 180 degrees. So this is 180 degrees minus angle EBC, okay, plus angle ADC, and this is equal to 180 degrees. So, of course, it means that 180 cancels 180 if you subtract 180 from both sides. So you see that angle ADC is equal to angle EBC. So if you transfer this to the other side, it becomes like this. So that's easily proven based on, I mean, you can prove in different ways, but so you can always find a way to prove. So I mean, that's very easy to work with, like that. So that's what the proof looks like right here. So exterior angle at B is supplementary to the interior angle. So angle EBC is 180 minus angle ABC. So from theorem 4, which is cyclic quadrilateral, angle ABC plus ADC is 180. So 180 minus angle ABC is ADC, and this is EBC. So EBC is ADC easily. So the worked example here, in a cyclic quadrilateral, ABCD, angle D is 68 degrees. Side AB is extended at B. Find the exterior angle at B. The exterior angle is, of course, just 68 degrees. So there's no point. Of course, if you need, you may need to show it. So draw the cyclic quadrilateral, fix the 68 degrees, and then use this logic of opposite angles of cyclic quadrilateral is 180, and you get one angle there. Then subtract from 180 again, and then you get the 68. Should I just okay? Let me just demonstrate what I mean by that to make it as clear as can be. So imagine we have a cyclic quadrilateral, this now, and this is center O. I mean, you can always label anyhow you like, A, B, C, D, right? Let me remove. So, I mean, we have our B here now. So it says that angle D is 68 degrees. So this angle is 68 degrees. And the question is, AB is extended at B. Find the exterior angle at B. So if we extend this now, we are looking for this angle. Okay? We're looking for this angle. So let's call this E like we did before. Of course, we know that angle so now this is CDA angle, or let's just say D, or let's say angle CDA. Yeah, angle CDA plus angle, this is CDA now, angle CBA. Okay, angle CDA plus angle CBA will be 180 degrees. Okay, that's opposite angles cyclic quad. Okay, that's a short way to go. And then CDA we know is 68 degrees. And what else? CDA 68 and CBA we can find now because this is 180 degrees, everything together. So angle CBA now is equal to 180 degrees minus 68 degrees. And that is simply 112, I believe. Yeah, that's 112 degrees. That is CBA. Now we go another step. So now we know CBA to be 112 degrees. So now we now need this angles, angle ABE. So we know that angle CBA plus angle ABE is equal to 180 degrees. The reason now is different. That's angles on a straight line. Sum of angles on a straight line. Angles on a straight line. Or you can just say straight angle. Angles on a straight line, which add up to 180 degrees. So we know CBA now to be 112. So 112 degrees plus angle ABE, which is the exterior angle, is equal to 180 degrees. So angle ABE is simply equal to 180 degrees, which is 112 degrees. And the answer again, yeah, we are back at 68. But because if you already know this, especially if you're not answering a theory question, just pick 68 and get out. Like, don't waste your time. But if it is theory, you may have to just show what I've just done now. So again, tangent. So theorem 6, tangent is perpendicular to the radius at the point of contact. So a tangent is perpendicular to the radius at the point of contact. Now, see what we are saying now. So if a tangent touches the circle at T, and O is the center, then OT is perpendicular at tangent at T. So the angle is 90 degrees. So the angle is 90 degrees. So a quick recognition, radius to the point of tangency makes a right angle with a tangent very easily. So this is a very straightforward statement. Imagine that you have the circle, the center is O here, and then you have a tangent. Uh, okay, let me use another marker. Say you have this tangent just touching this point now. So we are saying that if this is point T now, okay, uh, or okay, this is center O. So if you draw this line to meet the tangent, so it will be at right angle to the tangent. So that's what that theorem is about. So, and if you from the proof, so from the proof, we have this. So if T is tangent at point T and O is the center, okay, this is point T now. So this is the tangent. That line is a tangent. Okay, so yeah, this is all the story I want to be following. So I'll just read through and then try to do whatever I need to do as I read. So this is 90 degrees for sure. That's what the theorem is telling us. So um, if T is the tangent at point T, all right, um, so even if we go by contradiction and assume that this OT now, OT is not perpendicular to the tangent. So if you go by that, line at T. So we drop a perpendicular from O to line T, meeting it at M. So if you drop any perpendicular, I mean, still the same thing. So OM now. So if you even forget this and then still drop another perpendicular line, which will still overlap with this thing. So OM is still is now perpendicular at T. At least that's clearly perpendicular. If we assume this is not the first one was not even perpendicular. So perpendicular from a point to a line gives the shortest distance to that line. So OM is less than OT. If we assume that, because that's we are trying to prove by contradiction. So, but OT is the radius, right? So this distance from O to the circle at point T. So if OM is less than OT, then point M lies closer to O than the circle does, meaning M will lie inside the circle. Since M is on line T, this would mean line T passes through the interior of the circle. So it would cut the circle at 2 points, contradicting that T is a tangent, which touches at exactly 1 point. Therefore, by contradiction, we prove that the assumption is false and OT is actually perpendicular. So we are simply saying that any line you draw tangent to a circle, it is perpendicular to the radius of that circle. Simple. So if you like, let the tangent come from here now. If you like, draw your tangent here. So if you draw the radius to it, it will always meet at 90 degrees. So that's the deal here, right? So and that one too, we don't have to sweat too much about it. We have a single worked example on that. So a circle has center O. A tangent is drawn at T. Find the angle between OT and the tangent. That's 90 degrees. Don't even stress yourself. So a tangent to a circle and its radius meet at an angle of 90 degrees. They are perpendicular. That's simply what we are saying. So theorem 7, tangents from the same external points are equal. All right. Tangents from the same external points are equal. So if from an external point P, tangents touch the circle at A and B, then PA is equal to PB. Then the quick recognition is that two tangents drawn from the same point outside the circle. All right. That's the way to quickly recognize this theorem. So the proof, if tangents from external point, okay, I mean, this is what we are saying right here now. Now we have a circle. So imagine we have this circle, all right, with center O, and then you have an external point. Let's say we have an external point here. Let's say this is P, and a tangent is drawn from here to meet this circle at point A, and then another tangent is drawn from this point to meet this circle at point B. So we are saying that PA is equal to PB by rule. So that's simply what that is saying. And then so we can follow the proof. So, um, so we follow the proof using congruent right triangles and everything. So this is what the proof looks like. So I'm going to read through that as I try to work with the object we have. So this is what this is saying, that PA is equal to PB. So from the proof now, we say that we first of all we join OA, we join OA, OB, and OP. So join OA, join OB, and join OP. Okay, that's a nice, a smart way to handle this. Of course, you can see this is radius, this is radius already. Okay, so it means we basically have so that radius is common to the two of them. So we have similar triangles. But let's see what the proof says. So we after joining that, so from theorem 6, so we know from theorem 6, right, that when a tangent touches a circle, right, it makes an angle of 90 degrees. It makes an angle of 90 degrees with the radius. We know that. So we know that. So triangles OAP, so triangles OAP, triangle OAP, and triangle OBP, this triangle OAP, triangle OAP, and triangle OPB are right angle triangles. So they are similar triangles. And interestingly, I think we looked at similar triangles in a previous video. So in this case now, they are similar triangles. So they both have 90 degrees each settled. So another thing is that also OA is equal to OB. Okay, this OA now is equal to OB. So let me bring this one here. This is O. So we also know that OA is equal to OB because they are both radii. Okay, they are both radii. Two radius. Radius in two places. We said radii. So they are both radii. That's established. So an OP is common to the two of them. Okay, OP is common to the two of them. So two triangles OAP and OPB have hypotenuse. So the hypotenuse is the same. Okay, and then they have this as the same. So we can simply say OAP is similar to OPB. All right. Therefore, we can say triangles OAP and OPB are congruent. So OAP and OPB are congruent, or if you like, you can say they are similar. But already they have the hypotenuse and the radius and this basis in common. So automatically, AP will be equal to PB. So AP is equal to PB by congruency because uh, so this is equal to this hypotenuse is equal for the two. So automatically, it only makes sense for the two other sides to be equal. And that's simply what that is about. So let's go ahead and look at the worked example under that. So here now, if PA is equal to 12 cm, find PB. Easy. PB is 12 cm, so don't even stress yourself. So as far as you know, they are coming from a common point P. Then example 2, PA is 3x plus 2. Find and PB is 5x minus 10. Find x. Just equate the two. So 3x plus 2 is equals to 5x minus 10. So collect like terms. So you have 5x minus 3x, 2x, 2 plus 10, 12. So x is equal to 6 easily. And we move on. So theorem 8 now. For theorem 8, so it's talking about alternate segment theorem. Alternate segment theorem. The angle between a tangent and a chord through the point of contact equals the angle in the opposite segment. So if the tangent at A meets chord AB, right, then the angle between the tangent and the AB, that's ACB, where C is on the circle in the opposite segment. So the angle between the tangent and AB is angle ACB, and C is on the circle in the opposite segment. So quick recognition, you have a tangent plus a chord at the same point. Okay. Um, so the angle between a tangent and a chord through the point of contact equals the angle in the opposite segment. So this is the picture here. So sometimes the picture you may not really understand what's happening until you try to draw things. So you have a circle, center O, and then let's say you have a chord AB, I believe. Yeah, it says alternate segments theorem. So the angle between a tangent and a chord through the point of contact equals the angle in the opposite segment. So imagine we have a So the angle between a tangent and a chord, we already have our chord AB now. So let's try to draw the tangent. So let's say the tangent is passing through is like this now. Okay, so the meeting point, the line is here. So the question is, if the tangent at A, okay, well, I can reverse it to meet up with what we have here. So we have AB. That's okay too. So if the tangent at A meets chord AB, right, then the angle between the tangent and the chord AB, that's ACB. Okay, let's say this is C now. Because C is on this circle in the opposite segment. So this is C. So it means we have this. So this comes now, and we have this. So the angle ACB. So the angle the angle between tangent and AB. This is the tangent and this is AB. So this angle, now we're saying this angle now is the same thing as this angle, basically. So that's like alternate segment theorem, right? So the angle between the tangent and the chord is equal to the this other angle right here. So let's see what the proof looks like. So the angle between the tangent and the chord, okay, that's the statement of the proof. So using theorem 1 via central angle, so the angle between tangents, the angle between the tangent, okay, and AB, let's say this is theta now. That's all this is saying. So since we know that OA, this we know that OA now, if you draw this now, we know this OA is automatically perpendicular. So this OA is perpendicular to the tangent. That's from the theorem we just looked at the other time, because that's radius, right? So OA, we know OA is perpendicular to PA. So let's say this is coming from an external point. So let's say this is coming from P. So OA is perpendicular to PA like that. So from theorem 6, that's established. The angle between OA and chord AB, the angle between OA and the angle between OA and chord AB, this chord AB now, chord AB. So this angle right here, of course, uh, okay, I mean, we also have this one. So this is also right angle, right? So this angle now will simply be 90 degrees minus theta, okay? Because this is theta again now. Okay, yeah. So this angle right here will be that's the angle between OA, this angle between OA and chord AB, this right here, because this is also a right angle. So um so it's the same angle we also have here, right? So this angle is 90 degrees minus theta. It is 90 degrees minus theta, like that. Mm, so in isosceles triangle now, so in isosceles triangle AOB, so AOB, so this is, if you join this up to, this is an isosceles, this is automatically an isosceles triangle because this radius is equal to this radius. So in this isosceles triangle AOB now, this is also uh this will also be 90 degrees minus theta because this is radius base angles of radius. So this is 90 degrees like that. So of course we can easily get this part, this angle. So to get this angle now, so angle AOB, so angle AOB will just be will be 180 degrees minus 90 degrees minus theta minus 90 minus theta. So that'll be 180 will cancel all this. So we just have okay, minus like that, right? So that'll be theta plus theta at the end of the day. So this is just simply 2 theta, right? That'll be 2 theta. And from the theorem 1, we can then say that angle BCA, if you like, or if you like ACB, angle BCA or angle, no, angle, this angle BCA now, or if you like angle ACB. So angle BCA is equal to angle AOB divided by 2 from theorem 1, theorem 1. tells us that because angle subtended by an arc at the center is twice angle at the circumference. So it means angle at circumference is half of angle at center. So this here now, right? So an angle AOB now is 2 theta. So 2 theta over 2 is simply theta. And what is that theta? That's the same angle we have right here. So that establishes that idea. Okay, so that's alternate segment theorem now. Okay, so that's everything I've been through here. These are the steps. So you want to look at it yourself and follow step by step with the circle drawn and then follow all the lines. So the angle between the tangent at A and chord AB is 41 degrees. Find ACB. Of course, ACB is 41 degrees straight up. The angle, if ACB is 73 degrees, find the angle between the tangent at A and chord AB. 73 degrees also. So that's alternate segment theorem. So we go for theorem 9, which says that equal chords and related facts. So if we have equal chords and related facts, so here we have two statements. Equal chords subtend equal angles at the center, and that makes sense for sure. So if chord AB is equal to chord CD, then angle AOB is equal to angle COD. Okay, so we can start with that, right? So imagine this now. Equal chords subtend equal angles, and that's easy to comprehend. Imagine you have this chord AB now, and you have another chord CD, and we're saying that AB is equal to CD as the chord now. So this is center O. So imagine if you have this angle and this angle. I mean, if you draw this line, bring this and pull this, bring this and have this. Okay. So if you go like this now, so this subtend this angle, this subtend this angle, right? We are now saying, I mean, this is already looking like vertically opposite angles even. So we can easily say this is equal to this. But there are other ways to prove it, right? Let's see what the proof looks like here. Okay, well, I mean, that's the first statement. Let's look at the second statement. Maybe they are kind of corollary. Equal chords are equidistant from the center. Aha. So equal chords are equidistant from the center. That should make sense because we're now saying that this chord CD now, the distance from this center is the same thing as the distance of chord AB from the center. So because they are equal chords, right? So we have the two in one like that now. So let's go ahead and explore this possibility. So what do the proof say? Let me look at there are two statements. So for the first proof, very straightforward. If chord AB is equal to CD, then angle AOB is equal to angle COD. I mean, that's really easy. So angle AOB is equal to angle COD. So that means this angle AOB is equal to angle COD right here. So and the proof for that is consider triangles AOB and COD. So if you look at angle AOB like this and angle COD that way, okay, that's what we're considering. Then OA is equal to OC, OB is equal to OD, and AB is equal to CD given. Okay, so again, we have this. So I'll read the proof, right? So we know that it is established, of course, that this is equal to, okay, I need to change the marker. So this and this are the same because they are both radii. This is also equal to this. They are both radii. And as a result of that now, the angle here is equal to the angle here. And of course, the same angle is what we find here. So if you add these two angles and subtract from 180, what you get here is exactly going to be the same as what you get right here. Okay? So since triangles AOB and COD are congruent by side, because this side and this side, this side and this side, automatically the third side also will also be equal like that. So hence corresponding angles are equal. So we say this angle is equal to this angle easily. So that takes care of the first one. The second one is talking about that if you have chords that are similar, that they are equidistant, they have the same distance from the center of the circle. That's what the second one is talking about. Equal chords have equal perpendicular distance from the center. So if chord AB is CD, then OM is perpendicular to AB and ON is perpendicular to CD, then OM is equal to ON. Of course, that's really true. So from theorem 9 now, M and N are midpoints of chords AB and CD. So AM is AB over 2 and CN is CD over 2. Hence, AM is equal to CN since AB is CD. Now look at right angles OAM and OCN. We have OA equals OC radii. AM is CN shown. Both are right angles at M and N. So thus triangles OAM and OCN are congruent by right hand side. So OM is equal to ON. So let's come to the figure, and I'll go through that again so you can understand what I'm trying to say. Or better still, I can draw another circle with center O. So you have a chord AB and another chord CD, which we say this line is equal to this line, like that. Okay. So, and we're saying, so what this second statement is saying is that equal chords have equal perpendicular distance from the center. So you have this and this now. So you're saying that this distance is equal to this distance, basically. Okay. So if chord AB is equal to chord CD and OM, so the center is O, right? And OM is perpendicular to AB. So OM is perpendicular to AB. Okay, let's say this is M, right? OM is perpendicular to AB and ON is perpendicular to CD. So let's say this is N now. This is also perpendicular to CD, like that. Okay, that's the deal. From theorem 9, of course, M and N are midpoints. Okay, M and N. So this M now, of course, will be a midpoint. This will also be a midpoint. Okay, so uh since that is the case, then we can say that AM is equal to AB all over 2 for sure. And of course, CN, this CN now is also CD over 2. In that, and since AB is equal to CD, we can then say um, AM is simply equal to CN. AM is equal to CN, like this now. Of course, since it's halfway to, so these ones two are also exactly the same. So that's established. And beyond that now, we can now say that if we look at right angle triangles OAM, so we have OAM like this, and then OCN like this now. So they're both right angle triangles because this is a right angle right here. This is a right angle right here. And they both have the same, this distance is equal to this distance basically because these chords are of the same distance. So AM and CN, this AM and CN are the same also. These are the same. So automatically now, these are both right angles triangles at M and N. So those triangles OAM and OCN are congruent. And we can then say that OM, this OM now is equal to, so OM finally is equal to ON. And that's what we're trying to prove, that if these are perpendicular, then they are of equal distance from the center of the circle, basically. So, and I mean, that goes easily if we get to the worked example. So for the worked example now, um, so chord AB is equal to cos CD. If AOB is 92 degrees, find COD. Of course, COD is going to be exactly the same thing. So if AOB, I think this comes from this particular part now. If AOB is, whatever AOB is, this is, well, because we've established that previously. So they are both the same. Then we have theorem 10. We're still going to theorem 13 or so, or 12. So theorem 10 says perpendicular from the center to a chord bisect the chord. So statement, if OM is perpendicular to AB, where OM is the center and AB is the chord, then M is the midpoint of AB. So this one is linked with the proof we just looked at now. So that any perpendicular line you draw from the center to a chord bisects the chord. So like that. So if OM is perpendicular to AB, where O is the center and AB is the chord, then M is the midpoint of AB. So AM is MB. So quick recognition, you have a radius or line from the center which meets a chord at right angles. So look at this now. So for theorem 10 now, I know it carries a bit of resemblance with what we just did now, but let's look at that. Theorem 10, perpendicular from center to bisect a chord. So you have your circle, center O. That's the first thing you want to do every time. So then you have a chord AB. I mean, it can be anywhere. So you have a chord AB. You can draw it in any direction. So you have a chord AB like that, and you draw a line from here to here. This is M now, and you ensure that this is perpendicular. So we are saying that AM is equal to MB because any line you draw from the center to meet a chord at 90 degrees automatically bisects the chord. Then the corollary is that if you draw a line to bisect a chord to the center, it will also uh it will automatically be at perpendicular line, be perpendicular to the chord. So that's that. So if you look at the statements of the proof, right? So here we have that the statement, if okay, I mean this is a statement now. The proof now, consider triangles OAM and OBM. So OA and OB are radii, OM is common, OMA is equal to OMB, which is 90, given perpendicular. So triangles OAM and OB are congruent, hence corresponding sides are equal. So I mean, let me show you from the circle now what I've just done now. So here, so for the proof, we say that OA is equal to OB. Of course, that goes without saying because this is radius and this is radius. Okay, this is radius and this is radius. This are the same. Basically, they are both radii because it's from the center to any part. So this is radius and radius like that. Then OM is common to them. So we automatically have congruent triangles like that. So that means that triangle. So they are. So we say that, and of course we know this is 90 degrees given from the beginning. So it means that triangle OMA is similar or better still. I mean, these are 90 degrees, I mean, it's established, right? So we're saying that triangles OAM is similar to triangle OBM. And if that is the case, this side is equal to this side, this side is equal to this side, automatically AM is equal to MB. And that goes, the logic is established, okay? So the worked example is easy. So you have chord AB is 18 cm, then you draw a line OM to meet AB, just like what we have here now. So you have OM to meet AB, and then what's the deal? So find AM. So AB is 18 cm. So if OM is perpendicular to AB, automatically, so what AB that is 18 cm, this whole 18 cm now, is just going to be divided into 999 cm like that. So based on the theorem, so you have that division happening like that. Then we have theorem 11, gradually coming to an end, although the video is really long, but it's okay. I think this is a one-time justice for circle theorems, which is not a bad idea at all. Okay, so intersecting chords inside a circle. So if you have chords intersecting inside a circle, these are another thing. So if chords A, B, and CD intersect at X inside the circle, then we say that angle AXC is equal to half of the arc AC plus half of arc BD. So this theorem is often used when arc measures or central angles are given, right? So now we're beginning to talk about the idea of arc measures. So imagine okay, we have the proof here. So first of all, we use inscribed angle equals half arc. So the inscribed angle is equal to half of the arc, idea from theorem 1. So angles standing on the same arc are linked to central angles. So let the measures of arcs AC and BD correspond to angles AOC and BOD. So from theorem 1, any inscribed angle standing on arc AC is half AOC, and similarly for arc BD. So a standard angle chase shows angle AXC equals the sum of two inscribed angles that intercept AC and BD. So it becomes half of the sum of the two central angles like this. So since central angle measures their arcs, this is angle AXC, which is half arc C plus arc BD. Okay, let's try to demonstrate that as much as possible. So imagine now that you have, so we're talking about we're talking about intersecting chords inside the circle. So talking about the arc rule now. So imagine you have your circle, center O, right? Before I even do the center O, it's better to get some things out of the way. So, um, so chords A, B, and C, D intersect. So imagine you have a chord A, B, and you have another chord CD intersecting. So chords A, B, and CD intersect at point X. This is the center O. So the question now is angle AXC. AXC. This angle right here. This angle right here. We are saying that that angle AXC is equal to half of arc AC. So this is arc AC right here. Arc AC, plus arc BD. So this is arc BD right here. Okay, so now we set on for the proof. Angles standing on the same arc are linked to central angles. So the angle, whatever angle you have here, so this is an arc right here. So if you project this to the center, okay, so whatever angle you have inside this arc is going to be, so the angle here is, this angle is double whatever you have for the arc. Okay. Um, so I mean this arc right here now. So we know that that double thing is there. Then of course for arc DB also. So if you project something to the center like this, if you project something to the center this way, you also have this kind of angle here. So see what happens. So the angle, so the measure of this angle DB now. So we know that this arc AXC, I mean the angle AXC here, this angle right here is what our focus is on, right? So um let the measures of arc AC and BD correspond to angles AOC and BOD. So we have AOC and BOD. Those are the measures of, so measure of arc AC, all right, measure of arc AC is A angle AOC. Measure of arc BD, okay, is angle BOD, which I've indicated like this. So if that is the case, the next thing from theorem 1, any inscribed angle standing on arc AC, so any inscribed angle standing on this arc AC now will simply be half arc AOC, half angle AOC, and similarly for BD, we have half angle, half angle BOD, like that. So a standard angle chase shows angle AXC, this angle AXC right here now. Okay, so we can have this, we know that this, whatever angle this is going to be half of whatever we have here, right? So a standard angle chase shows angle AXC equals the sum of two inscribed angles, the sum of two inscribed angles that intercept axis AC. So it intercepts axis AC, right? And BD, like that. So you see, we have arc. So this is from BD, this is from AC. So we have that intersection going on right there. So in that case, it becomes half the sum of two central angles. So it becomes half the sum of the two central angles. So that we now finally say that angle AXC now is equal to half into half of angle AOC plus angle BOD, like that. And that is exactly what, so this is for arc AC, this is for arc BD. So we are using their measures now, and that's exactly the same idea. So we have that example right here. This one says that so for the worked example, the chords intersect inside the circle. The intercepted arcs are 110 and 50. Find the inside angle. So of course the inside angle will just be half of 110 plus 50. That's half of 160, which is 80 degrees. And that takes us to the last theorem. Yeah, thankfully, the last theorem. It's been a long journey, but let's see. We are up, we're almost done. So, angle formed outside the circle, uh, talking about maybe from 2 seconds or from seconds or tangents. So, an angle formed outside the circle equals have the difference of the intercepted arcs. So if the arcs are A degree and B degrees with A bigger than B, then the angle between them is the angle formed will be half. Angle formed outside the circle will now be half into A degree minus B degree, like that. So, and this is the statement of the proof now. Let an external point form two lines cutting the circle, intercepting arcs with measures A and B. So construct inscribed angles that subtend each arc. By theorem 1, an inscribed angle subtending arc A has measure A over 2, and one subtending arc B has measure B over 2. It's a bit related to what we just did. So the external angle equals the difference of the two. So now this one, I'm just going to go straight and do what this is about. So let's see that right here. So imagine for that theorem 12 now. Theorem 12 is saying that if you have a circle center O as usual, right? And then you have an external point, say an angle formed outside the circle equals half the difference of the intercepted arcs. So imagine you have this line, this is a secant now because it's touching the circle at 2 points. And then you have another one like this. It's also a secant touching the circle at 2 points. So you can see now that we have two arcs. These two arcs caught by these two things now. So, and let's say this is what should I say now? Um, so what we can do here, let me shift the center to somewhere like this. Let's say this is center O. So one thing we can do right here is to join. Okay, we don't even need the center there. So let the center be where it was. Okay, we have our center where it is. So one thing we can do right here is to just say we join this up together. So, and you see, this is the bigger arc now. And the measure of that arc is angle A, which is bigger than the measure of this other one now, which is B. Okay. So, and from what we know about arcs subtended like that, so you discover that, this angle, this arc now, whatever it makes at the center, okay, um what about, let me change this now. What about if we have this now? We have this. So the measure of this arc now, based on what we have, is A degrees. So automatically, the same arc now is going to make A over 2 on the circumference, A over 2 degrees on any part of the circumference. That's that. Then for this arc now, if you also take it to the center like this, you have this. So it makes B degrees like that. So the same arc here we just come and make B over 2, right? So at the end of the day, what we are saying is, if this is a point P, this angle now is what we are focused on. This angle is what we are focused on and we say that this angle will end up being half of A minus B, right? So, but I mean, that is going to make sense. Look at it already. So imagine you now have this. So it can be really messy, but let's see. This is this, this now, and this. Look at that green stuff. So we already have B over 2 here based on theorem 1. So you can see this whole angle now will be 180 degrees minus A over 2. And then we are looking for, let's say this is what we are looking for now. We're looking for X. Let's that be X now. So this is easy because from this triangle now, we have three angles, 180 minus A over 2, then B over 2 and X. So that X now is just going, we are just going to have X plus B over 2 plus 180 minus A over 2. All of that is equal to 180 degrees, basically. So from this green triangle now. So you see, this just cancels this easily. So X now, if you transfer this to the other side, that is A over 2. Then B, transfer it to the other side, that's minus B over 2. So that means that X, the angle formed outside the circle is now X, which is half into A minus B. And that is exactly what that theorem is telling us now. So if two secants or even two tangents form an arc outside, form an angle outside of a circle, that's the deal you have right there. So that's what we have here. So you see, it's half into A minus B based on what I've proven. So in this case now, so if you have 2 seconds form an outside angle, so the intercepted arcs are 150 degrees and 70 degrees. Find the outside angle. The solution is simply just say half into the big one, that's 150 degrees minus 70. That's half of 80 degrees, which is 40 degrees. So that's the kind of thing we have established here now, that this X now is simply half into A degrees minus B degrees, like that. All right, so this is a long video, but it's okay. Especially it is a one-stop shop for circle theorems. So now if you are solving problems on circle theorems, you have to pay attention, like from everything I've been doing. Mark the center O and identify any diameter. And that's the first thing we do. Mark the center O, then circle any tangents. If you have tangents, mark right angles with radii to tangency points. So like anywhere, maybe you have a radius meeting a tangent, you already know that's 90 degrees and things like that. Then look for same chord. So if you have same chord, like same segment angles are equal, so you can easily figure that out. For cyclic quadrilateral, where you already know that opposite angles sum to 180 degrees, and then tangent plus chord, you have alternate segment theorem like that, so that the angle between a tangent and a chord is equal to the angle in the opposite side of the circle. Then you can use triangle angle, which sum to 180 degrees to finish. That's a lot. We use that a lot. Then keep track of what arc or segment or chord each angle subtends. So it is always important to pinpoint the angle, the angle any arc or chord subtends. Very important. So that leads us to these 10 practice questions. So try your hands on this because you need to really master it because those proofs can be quite confusing sometimes. But the more you try, the better for you. So try your hands on this very important, very nice questions, and let me know how helpful that is for you. So thank you so much for listening. Let me know if there's something else you'd like me to try out. If you have subscribed already, I thank you very much for doing that. If you have not subscribed, why not go ahead and do that right away? Um, and hit the notification bell also so you can always get alerted each time a new video is released. Having done that, you can, of course, become a member of this channel by clicking on join, and that gives you some special privileges. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.